In this video, we will talk about kinetic energy. Say we have a mirror and a stone. At first, we take the stone and we put it gently on the mirror. Nothing happens. Then, we remove the stone and we throw it onto the mirror. The mirror breaks. The only thing that changed from the first case to the second is that in the second case, the stone was in motion with respect to the mirror when it received a certain amount of energy, which made it break. So, this type of energy results from motion. Therefore, it is called kinetic energy, since the word kinetic comes from the Greek word kinetikos, meaning of motion. The kinetic energy Ke of an object depends on the mass of the object as well as its speed. It is equal to half mv squared, where m is the mass of the object and v is the speed of its center of mass. The kinetic energy for rotational motion is given by the formula Ke equals half I omega squared or half I theta prime squared, where omega is the rotational or angular speed and theta prime is the rotational or angular velocity. And as we said in a previous video, work is a transfer of energy. So in the case in which work is done on a system and the only change is in its speed, the network equals the change in kinetic energy of the system. This is known as the work energy theorem or work kinetic energy theorem and is written as sigma W equals delta Ke, where sigma W is the network or the work done by the net force, and delta Ke is the change in kinetic energy. Delta Ke equals Ke final minus Ke initial. Example, a car considered as a material point of mass 1300 kilograms moves on a straight and horizontal road at a speed of 20 meters per second. The driver brakes and the car stops after traveling a distance d. Determine d if the net resistive force, which results from braking, has a constant magnitude of 5,000 newtons, knowing that the work done on the car only affects its speed. The studied system is the car. The reference is terrestrial. The forces exerted on the system are mg, the weight of the system, n, the normal reaction of the road, and F, the net resistive force. Applying the work energy theorem, we replace the network sigma W by Wmg plus Wn plus Wf, and we replace delta Ke by Ke final minus Ke initial. The work done by the weight and that done by the normal reaction are equal to zero since these forces are perpendicular to the infinitesimal displacement at any instant. In addition to this, final kinetic energy equals zero because the car eventually comes to a complete stop. We get minus Fd equals minus half mvi squared, which gives d equals mvi squared over 2f. We plug in the values in the last equation and get d equals 52 meters. And this is all for this video. Thank you for watching.